Today our topic is diffraction. What is diffraction? When there is an obstacle and you allow to a wave to incident on it, the wave bends at the edges, and this bending of wave along the edges is known as diffraction. This phenomena takes place only when the wavelength of the wave and the thickness of the obstacle are approximately of the same order. And there are two types of diffraction. One is known as Fresnel diffraction and another is known as Fraunhofer diffraction. What are the differences in between these two diffractions? In Fresnel diffraction, the screen and the source are at finite distance. It means if this is your screen and this is your obstacle and this is your screen, and when the source is allowed to fall on the slit, the distance between the slit and the source is finite, as well as the distance between the slit and the screen is also finite. Second, we don't use any type of lenses in case of Fresnel diffraction. Third one, in case of Fresnel diffraction, we use cylindrical and spherical wavefronts. What do you mean by wavefronts? Let us consider you have a point source, and we know that point source allow to all waves to move in all the directions, and waves are moving in the form of crust and troughs. Let us consider this is the wave at an phase angle of 90 degree. This is the second wave at a phase angle of 90 degree. Now we will find out all the points which are in same phase, and when we connect all these points we found a imaginary surface, closed surface, and this is known as a wavefront. It means every point of the wavefront at same phase difference, the angle between the phase is change is 0, and every point at the one wavefront behaves like a source for the another wavefront. When we see from A dash to A, we find out the wave is coming from A. It means the primary wavefront behaves like a source for secondary wavefront. And how will you get cylindrical and spherical wavefront? If you have point source, you will get spherical wavefront. And if you have a small cylindrical source, then you will have a cylindrical wavefront. How will you obtain a plane wavefront? Let us consider you have a source having large length as compared to the thickness. And when you get this source wavefront, we find out that you will get a plane surface when you connect all the points which are in phase. This is known as plane wavefront. Now this is the third point of the Fresnel diffraction, where we find out that only cylindrical and spherical wavefronts are used. Fourth point, the magnitude of the amplitude or the brightness of Fresnel diffraction does not depend upon angular displacements. It means if we are observing the effect of the diffraction at any point P, then if the source is or the wave is coming perpendicular to P or within some angle, the angle will not affect on the diffraction pattern obtained at the point P. The fourth point is the amplitude at point P of the diffraction pattern only depends upon the distance of the source from the screen. If the distance changes, the magnitude or the diffraction pattern maxima or minima will change. Second type of the diffraction is Fraunhofer diffraction. In case of Fraunhofer diffraction, the source, the screen are placed such that they are at an infinite distance. How will you take source and screen at infinite distance? It's very simple with the help of use of convex lens. The source is placed at a focal length of your convex lens, then you will obtain parallel beam, parallel rays, and these parallel rays seems to be coming out from infinite distance. These parallel rays are allowed to fall on a slit, and again when there is a bending of beam, these are again focused on the screen with the help of another convex lens. In case of Fraunhofer diffraction, we are using convex lens to make the source away or at an infinite distance from the slit, and second convex lens is used to converge all the rays at a point on the screen. So these are the two types of your Fresnel or diffraction, that is Fresnel diffraction and Fraunhofer diffraction. Now we will deal with Fresnel diffraction. In case of Fresnel diffraction, we take some assumptions. First, we are here assuming that all the primary wavefronts behaves like a source for the secondary wavefronts. And now the second assumption is that the angular change can change the effect. It means if the light is coming straight, it will give maximum brightness, and if the light is coming with some inclined angle, the brightness and the effect will change at a given point. Third is the wavefront is allowed to divide into large number of half period zones. Now, what are half period zones and what are half period elements? We have discussed about the plane wavefront, and in case of plane wavefront, we know that we obtain a plane wavefront with a thin and long source of light. When we find out all the points which are in phase, we find out that in 3 dimensions we will obtain a plane wavefront at every point of which all the points of the wave are in same phase. And let us consider if we are giving it A, B, C, D, the plane wavefront. It means every point of the plane wave front behaves like a source. Now, in half period zone, we take this plane wave front as our base. Let us consider this is your plane wave front, and every point on it behaves like a primary source. Let us consider O is the center, and at any distance B there is a point P where we are finding out the effect of this wave front. At a distance B plus lambda by 2. What is lambda? It is the light, or it is the length of wavelength of the wave used. Generally, in case of diffraction, we are using monochromatic source, and we have single wavelength for this wave, and the single wavelength of this wave, let us consider this is equal to lambda. When, and let us consider this point is denoted by m1. Similarly, let us consider and another point, and the condition is that now the m2 is at a distance of b plus 2 times of lambda by 2. It means every time we are increasing a distance of lambda by 2 separation from the point P, where O is the center, and OM1, let us consider this is your R1, and similarly OM2, let us consider this is your R2. Now take another similar points M2 up to Mn and so on. Why we are using this? Because we want to find out the effect of these waves which are coming out to the point P, whether we will obtain here maxima or minima. It means whether we are obtaining at the point P the bright pattern or dark pattern. It means the brightness and darkness depend upon these waves which are coming from a distance of b plus lambda by 2, b plus 2 times of lambda by 2, b plus 3 times of lambda by 2. We find it can be understood like this. Let us consider P point is taken as the center and B is taken as radius, and with the help of protractor we are drawing an arc at point O, and the another radius is B plus lambda by 2, and you will get at this point M1. Similarly, by opening the protractor B plus 2 times of lambda by 2, you will obtain the third point, that is M2. If we draw circles with the center O, radius R1, radius R2, radius R3 on this plane wave front, this is known as half period zone or half period element. What is the use of these zones? If we consider again the P is our observation point, and the distance of O to P is B, and the distance of the M1 point from P is B plus lambda by 2, then what is the average distance of this first half period zone, this area which is covered by this first circle. The average distance is given by b plus lambda by 2 and divided by 2, and we will find out that this comes out to be b plus lambda by 4. Similarly, if we find out the average distance of this second half period zone, then we have to take b plus lambda by 2 plus b plus 2 times of lambda by 2 divided by 2, and we will obtain the average distance b plus 3 lambda by 4. If we compare these two average distance b plus lambda by 4 and b plus 3 lambda by 4, there is a difference of lambda by 2. It means if wave is coming from first half zone and wave is coming from second half zone, there is a path difference of lambda by 2, or you can say that there is a phase difference of pi. And with the help of this calculation, we find out that at point P, you are obtaining a large number of waves which are superimposing at the point P. And according to the law of superposition of wave, we find out that the total amplitude y is given by y1 plus y2 plus y3 plus y4 and so on. The last wave, let us consider, that is yn. From our first half zone having radius r1 at a distance b, we are obtaining the wave at point P, and for this we can give the wave like this: y1 is equal to a1, where a1 is representing the amplitude of the first wave which is coming from the first half element, a1 sine of omega t minus phi, where phi is representing the phase difference. Second wave, that is y2, which is coming from the second half zone element. It means this portion. The wave coming from this portion can be represented like this: y2 is equal to a2. Now a2 is the amplitude of the second wave, sine omega t minus phi minus pi. Why pi is introduced here? Because we know that the difference between these two waves, the path difference in between these two waves is lambda by 2, and the path difference lambda by 2 gives a phase difference of pi. It means if from the first wave at point P we are having a crust, then from the second wave a trough is approaching. Similarly, y3, it means the third half zone, given as a3 sine of omega 2 minus phi, again introduce a path difference of pi, and so on we will obtain the last wave. If we solved all these, we obtained y, that is the total sum, is given as a1 minus a2 plus a3, so on. Alternately you will get the negative symbol, the positive symbol, and sine of omega t minus phi. The amplitude, this is the amplitude, and let us consider this whole term is represented by capital A. Capital A is representing the amplitude of the resultant wave. Then y is equal to a sine of omega t minus 5. Then how we will define a1 minus a2 plus a3 minus a4 and so on from the last half zone. A1, or we can say that a1 plus a3, and mean of these two is given by a2, because all the waves are not depending upon the area covered by the half zone. The amplitude of the wave is independent of the area covered by the half zone. Similarly, we will find out A4 is equal to A3 plus A5 divided by 2. If we put A2, value of A2, value of A4, and on calculation we will find out that A is equal to A1 by 2. It shows that if you have half period zone and you are finding out what effect is at point P due to this half zone, only this portion, it means this is your first half zone, and half of the first half zone shows the effect is equal to the total effect shown by your half zone plate. If you cover this with the help of some obstacle, it means you are not allowing the waves or the light from this part to fall from this part to point P. If you are covering this part, you will find out the darkness. Hence, due to this reason, if we compare the light waves and the sound waves, the light waves bends small, where the sound waves moves through the walls. Because of this reason, because area of this is given by, that is area of your first half zone, that is by r1 square, and the radius is of the zone, if we are talking about the nth zone, is given by nb lambda. If we put this in the above equation, we have to take n is equal to 1 for the first half zone. Then what will be the area? Area is equal to pi r1 square, and substituting the value of r1 from this, you will find out this is your b lambda. It means area of every half zone is same, because you are putting the value of pi r1 square. Next you will find out the value of, you will take the difference of the area of the second half zone and the first half zone. You will find out again the area of this part is equal to this part. It means all the half zone plate have same area. It means this shows the same effect at the point P, as the first half zone plate allows the waves to fall at point P, second half zone plate is doing the same. Hence, for sound waves, because lambda is very large and the effect coming from the half of the first zone plate, then we have to take the area is equal to pi b lambda divided by 2. In case of light, this lambda is very small, Hence, a small obstacle can restrict the light, but in case of sound waves, the lambda is very large. Hence, large obstacles are required to restrict the sound, which is not many times not possible, or many times we find out that this wavelength or this thickness of obstacle is commonly not found. Hence, sound waves can move through any obstacle, but light waves can't.